that sort of wraps up the physics of Bainite. I do want to hit this Acicular ferrite, right? Which is basically, these are ferrite plates that instead of forming nice layers, form this mess of disorganized plates. So here we have Bainite forming nice, regular. The subunits are fairly parallel. Acicular ferrite, they're just pointing any which way. I like the term acicular Bainite because it's more descriptive of what it actually is, rather than acicular ferrite, because it mimics Bainite quite a lot. They form very similarly, except Bainite forms in sheaves, right? And they nucleate from the austenite grain boundary and move out. Whereas acicular ferrite nucleates in the interior of the austenite grain, right? And so it nucleates with, it grows into this disorganized structure of plates because there is no, nothing forcing it to be nice and regular. Remember, Bainite forms the Kirchhoff-Sachs-like orientation relationship, right? And we see the same thing, right? We see growth, right? We're limited by the T0 carbon concentration, right? And so we're nucleating heterogeneously, sort of at inclusions. And so if we have a sample that forms acicular Bainite, if we, an alloy, if we like remelt this to remove the inclusion and we go through the exact same cooling schedule, we'll get Bainite rather than acicular ferrite. So it's really just Bainite that's nucleating interior to the grain rather than at the grain boundary, right? And if we increase the grain boundary surface area, we can do the same thing, right? So if we have big prior austenite grains, we get acicular ferrite. If we have small grains, right, a lot more surface area, right? Remember, surface area goes by what with respect to the radius? Right, squares, right? And so, right, we're making the grains a little bit smaller gives you a drastic increase in surface area, a lot more nucleation sites. So if we make our austenite grains smaller, we eliminate acicular ferrite. Right, this is very much like, think about it in the same way as you do about idiomorphic versus allotropomorphic ferrite, that diffusional ferrite, right? If you have lots of nucleation sites, you're going to grow ferrite at the grain boundaries, right? If you have inclusions and intermetallics in the grain, you're going to grow idiomorphic, right? Okay, so that we can also go the opposite way, right? If we make our grain boundaries ineffective as nucleation sites, right? Which means if we grow some allotropomorphic ferrite on it, right, a little bit of boron will do that, right? Drastically reduces the grain boundary energy, which means we have less favorable nucleation sites for Bainite. We'll go grow acicular ferrite than upper Bainite. Right? Okay? And so much like martensite, right, Bainite is, when I said lower Bainite's tougher than upper Bainite, the stuff's still not tough, right? You still have layers of brittle carbides separating, right? You've got plenty of places for cracks to nucleate. And the ferrite itself, right, the Bainite itself contains fairly small amounts of carbon. So the tempering is not as dramatic as it is when we look at tempering of martensite. But basically, if we have retained austenite, if our Bainite reaction doesn't go all the way to completion, we still have retained carbon and this retained austenite, and this austenite is carbon enriched. So if we temper it at temperatures where we have mobility of our carbon, this will decompose this enriched austenite into ferrite and other carbides. Right? Basically, we'll be like growing perlite within our Bainite. Right? This is, if we have strong alloying elements that are strong carbide formers, such as chromium, vanadium, molybdenum, and niobium, right? By tempering, we form more stable carbides than cementite, right? We form these intermetallic carbides, right? And these are much more stable, so we get a additional hardening, secondary hardening that comes from tempering the Bainite. And this is what sort of the tempered Bainite structure looks like, and optically, I mean, it looks like tempered martensite. You have to be really good to be able to pick out differences between these steel structures after they've been through a couple of heat treatments. Right. Okay, so last couple slides and we'll wrap up a couple minutes early. Okay, so role of the different alloying elements. Carbon, as you might expect, the amount of carbon in your system is going to have a huge effect on the range of temps over which Bainite forms, right? And you can think about that in terms of the shape of that T0 curve, right? So lower, right? And then in terms of other elements, are all going to basically have the effect of lowering the Bainite start temperature, right? So carbon, this is just a rough empirical fit that tells you what the Bainite start temperature is going to be as a function of your alloy composition, right? We can see carbon has the greatest effect, right? And then manganese, molybdenum, chromium, and nickel, right? All those alloying elements depress our Bainite start temperature.
So you just put like the weight percent number in the names of the elements?
Yeah. Yep. Right. I don't think you'll ever actually have to use this. It's just sort of I like it just because it's easy to, since someone went through the trouble of fitting it, it just shows you sort of what the relative effects are. That carbon has roughly 3 times the effect of the next greatest element at reducing the Bainite start, right? And the amount of carbide that you're going to form, you're going to have to balance by the amount of carbon, right? So the amount of carbide depends on the concentration of carbide. So we can't raise this up too much, right? Because we don't want to destroy our other properties, mostly toughness, right? So we have a optimal carbon concentration of about 0.4%. Okay. So in plain carbon steels, right, our Bainite reaction sort of hides behind rapid ferrite formation, right? So we have to add substitutional solutes to retard the ferrite and cementite reactions. Right? We talked about that in the perlite growth, right? So basically, that has the effect of pushing the nose of these curves in the TTT diagram over here to the right. So that means with a cooling curve, you can miss the nose of the ferrite curve and enter into Bainite, right? So if you just have plain carbon steel, if you cool, you're either going to have two things happen. You're either going to go through the nose, and then you're going to get a pearlitic steel, or you're going to go in front of it and hit martensite. In a plain carbon steel, it's very difficult to hit Bainite, right? But if we, by some smart alloying, we can push this to the right, come down into the Bainitic region, right? Still difficult because we need to avoid this martensite start, right? But we can push Bainite to the left with molybdenum and boron, right? Remember, boron is going to retard the ferrite reaction, oddly enough, by giving us a layer, grain boundary layer of ferrite that makes it difficult to nucleate perlite, right? But so if we play with these concentrations, and we're talking, very small amounts of boron, 0.002%, right? So this is, right, percent is 100, is hundredths, thousandths, 10 thousandths, 100 thousandths, so 20 part per million. Boron and less than 1 weight percent molybdenum, we can get fully Bainitic steels. So what the role that Bainitic steels play is we want cheap steels, right? So we need moderate strength needs with a low amount of alloying elements, right? So we want things that are cheap but still stronger than pearlitic steels, right? And that's basically the range we're playing in, right? And if we look at alloy compositions, carbon, silicon, manganese, molybdenum, boron, right? These become fully Banitic, very little martensite, using simple things like normalizing heat treatments, right? If we want to go through, this is basically just sort of like a flow chart of how we can, the range of Banitic steels that you can get, right? And sort of compositions, right? So our as we go up for each of those different classes, what the alloy compositions look like, right? And so you can think about the main categories of these. We can think about ultra high strength alloys, which are a mix of bainite, martensite, and retained ultra high strength alloys, right? And we get high hardening by this magical pixie dust composition here, basically allowing us to prevent cementite formation. Medium strength alloys, which we use in most of our forgings, in camshafts and crankshafts, and crash reinforcement bars, the pillars, in door frames and things like that for automotive use, fall into this medium strength alloy regime. Creep resistant bainite, creep resistant alloys. The main thing is we want to throw some chromium and molybdenum in there to enhance hardenability and to precipitate carbides, right? Basically, the more carbides that we have in there, the more that we're impeding defect motion at higher temperatures, the more creep resistant our alloy is going to be. And then there's this other weird class, which are inoculated alloys. Which we throw some non-metallics in there to give us heterogeneous nucleation of acicular ferrite, right? And those are used in places such as oil rigs, right, where we begin to we want enhanced properties of the fact that we have plates going in all different directions rather than layered plates, right? But for the most part, Bainitic steels are sort of fill this niche of moderate strength but very cheap to produce, right? There's a couple specialties, but that's really the range that we want to think of with Bainite.